All right, so let's start maybe. Good day, everyone, and welcome to MetaBuild, the first workshop for building the foundations of the metaverse. I'm very excited today because we had a lot of very good quality submission, and that led us to quite a varied program. As you may see in the chat, I posted the current rundown. So we will have very interesting talks relative to augmented reality, virtual reality, AI, IoT, and social computing. And following this talk, we will have a small Best Paper Award because we thought the papers were of such a good quality that we need to reward one of them, which was of excellent quality. And following that, a panel on building the metaverse from diverse perspectives. So without further ado, I let our co-host Likhan Lee to introduce.
Oops.
The paper.
Yeah, so today we have several works being selected as the first years of in the first year of the MetaBuild, and the papers we have 1, 2, 3, 4, 5, 5 in totals. And we will present the first paper, and the name is Scaling Up AR, University Campus and Physical Digital Metaverse. The presenter will be Tristan Brown. So Tristan, now the stage is yours. And I think now Tristan is trying to share his screen, and let me introduce Tristan. Tristan Brown is an assistant professor in the Division of Integrative System and Design at the University of Science and Technology. And Tristan got his PhD from the University Grenoble Alpes in France in 2016. Before that, he was an engineering student also in France, and also he received MSc in Italy. And his research focus is primarily AR and VR, with other interests in the pervasive and cloud computing, as well as human-centric system design. Now, Tristan, you can start now.
All right, thank you, Paul. Okay, so yes, as was introduced, today we will talk about how we can scale up augmented reality to very large scales, taking the example of our university campus. All right, so this work was done in collaboration with two other researchers in HKUST, which are Professor Pan Hui, who is a professor at HKUST, and Carlos Bermero Fernandez, who is currently a researcher. All right, so, well, I know it's a workshop at IEEE VR, so maybe not very necessary to introduce what augmented reality is, but just a quick summary of what we will consider as augmented reality in this presentation. So we consider augmented reality as a way to deliver digital experiences to human users in the physical surroundings and to augment the physical world with digital content. So examples that are the most famous are, of course, Pokemon Go and the IKEA app that allows you to place virtual furniture in your living room to see how it would look like in real life. And although, well, technically AR can use a ton of virtual content from all the perceptual channels, we will primarily focus on visual content. And finally, one very important thing is AR is a part of ubiquitous computing, and as such, it should guarantee seamless and lightweight user interaction with the digital entities that we're presenting. nowadays, there are many recent headsets that have good improvements, and they are lightweight, they can receive video and audio feedback, and they can merge the content, the digital content, with the physical world quite accurately. But in augmented reality in general, there remains one key challenge, and this challenge is even more important when we start to scale up to university campus or even city scale. And this is the detection and tracking to map the physical world and accurately display the content where it's supposed to be. And this is going to be the main topic in this presentation. All right, so
あ、しまった。ダメだ。
all right, so currently, most augmented reality applications are single user. Very few present collaborative aspects, and they present significant constraint in terms of time and location. Most applications nowadays work at room scale, and some of them can be semi-persistent, but there is nothing really for a large size environment with massively multi-user experiences. And what we want to develop is an integrated framework to enable the first AR campus metaverse by considering the nature of the various environment and the available sensing platforms. So typically, an example, so this is from an advertisement from an existing framework, but this is what we aim to develop, where we have massive mapping of large-scale areas and are able to precisely register the pose of the user in such environments. So currently, most development of metaverses in general and campus metaverses are focused on virtual environment and virtual reality. And here we want to exploit a bit more the physical digital duality that is brought by the metaverse. And so to do that, we think we need to go beyond virtual reality and consider extended reality and even more augmented reality to merge the digital content on physical scenes. And our key contribution in this paper is to define an integrated framework that implements this first AR campus metaverse. So what can we do exactly on an AR campus metaverse? Well, by merging the physical and the digital content, we can do many different things. The first obvious example is navigation, where we guide the user through 3D cues overlaid on top of the real world. This is what is represented here in figure C, where the route of the user is represented by orange bolts. And this is very good when we start to have intersections with verticality, like here, where traditionally a map would have trouble representing accurately where the user should go. We may also consider digital agents with artificial intelligence as digital tour guides. Another aspect is the access to the campus data, where we can monitor the usage of major facilities and provide real-time data to campus users. We can also digitally augment physical events and increase the presence of remote students, which has been a very big problem in Hong Kong, where we have some issues with traveling outside of Hong Kong. And finally, arts, game, and entertainment, where typically, as is shown in figure A, where we could have content displayed as a digital gallery in the physical locations. So summarized here, for navigation, we can guide the user or present AI agent. To access to campus data, we can provide location and context-aware visualization capabilities of IoT systems. We can introduce more physicality to digital events and more digitality to the physical events by augmenting them with digital content. And finally, we can provide digital entertainment activities and enable digital exhibitions. So, of course, besides that, Metaverse Campus should support learning, and there are different applications that we can deploy here, whether it is for medical school, where we could have medical content, 3D visualization, customized medical content editor, and see through AR to support medical activities. We could also have situated visualization for management, business, and production line capabilities. We can have robotic behavior editor for the engineering school, and also assistance for typical laboratories that we have in our School of Science and Engineering. Also, we can support two different kinds of learning modes, which is remote learning with a VR device for remote students, but also on-campus learning with AR device, whether it is augmenting courses through augmented reality or having a better sense of presence for remote students by displaying them in AR. So here is our proposed framework. And what we propose is a client-server architecture for an AR metaverse that relies on local and global mapping to register the camera pose and perform content placement, display, and edition. So first, we have a local map manager. So the local map manager would build maps of the environment using typical simultaneous location and mapping that take the camera frame and additional sensors and build a map on device. But at campus scale, we move across several rooms, corridors, and buildings in short amount of times. And the client devices are lightweight. They don't necessarily have memory and computational power to process the maps at such a large scale. On top of that, we have a ton of environments that are not working very well with typical SLAM techniques, like outdoor environment or large indoor environment. So what we need is not only multiple local maps to handle the scale of the campus metaverse, but also a correspondence to a global map that will map all of these environments. And this is what we have here, a global map manager. So this global map manager would be stored on the server, and this is to allow all clients to share the same map. So that would allow not only to have a persistent experience, but also a multi-user experience. This global map needs to be dense enough, such as high-density scans, and we should most likely use crowdsourcing to build and update the map. This map would then be combined with the local map to provide alignment, camera pose registration, and content display. So this is what I displayed here. This is one of the maps we built with a few people. So this is crowdsourced for 4 or 5 different devices. And this is the map from our university main building. It contains it was sourced from about 200-300 images and contains 12 million points. And this is only a very small area of our full campus. This is just the entrance and the main atrium. So now that we have a local and a global map, how do we register the local map on the global map? Because registration is a very computation-heavy process. If you do 2D registration, you can do feature matching, but with many images, it takes a long time. 2D, 3D registration is the perspective and point problem, which is also fairly computation-heavy, and even point cloud matching requires heavy computation. And these algorithms on top of that, their execution time increases exponentially with the scale. So typically 2D registration is an n-squared problem. The more you add images, the more time it takes. But what we propose is to do rapid registration on device through anchor registration and course localization. And then we use networked alignment and registration to perform the fine registration on the server. So anchor identification means to recognize physical anchors to rapidly identify the location of the user. So typically what we would have is objects, either 2D or 3D, that we recognize rapidly, either using bag of virtual visual world or fast machine learning techniques, like MobileNet or YOLO. And these allow to use the natural features of the environment, like typically a statue, a mountain, and to register easily for difficult environment, like outdoor or large-scale indoor. Then we can also leverage on the campus a ton of sensing capabilities to provide coarse localization. So even if we won't have the pose with that, we will have a good estimation of the user's location using Wi-Fi access points or even Bluetooth beacons. And typically in our university campus, we have a very dense deployment of Bluetooth beacons that can give your location with a meter accuracy. Then with this, with both this local and global map, we can register the local map over the global map using the alignment and registration manager. So the goal is to accurately locate the user in the global map and retrieve the content to be displayed. We propose to use different algorithms depending on the type of environment. For instance, if you have small and distinctive indoor environment, you can use iterative closest point algorithm. But if you have larger scale environment, you may need to require a much more efficient algorithm relying on machine learning techniques like PoseNet or HLOC. And you can also do triangulation if you have enough anchors. So why did we do previously coarse localization and registration? Well, this is to query a subpart of the global map and make it much more computation efficient. Of course, despite being more computation efficient, some techniques take still a lot of time. Typically, HLOC takes about 300 milliseconds to half a second when run on server. So we need to include some delay compensation techniques where we keep local tracking on the device and we correct the pose based on this local tracking. So of course, registration is only one aspect of the problem, and we need to provide tools for the users to be able to provide content. So to do that, we propose to have a content manager where users can put virtual content in the Meta Campus editor, and then the clients would gather the campus and display it perfectly aligned with the local map. So here is how we envision this content editor. Typically, the user would first record the venue, and this could be used to also participate in the crowdsourcing effort to improve the building of the global map. Then the user, once the area is mapped, can save the map and add the content to the server. And finally, other users can save the content, as you can see here. So of course, we are discussing a networked system on a very large size university campus, and we cannot afford to have only one server. So to address this issue, we propose a tiered edge computing architecture that splits the model storage update and the content storage of the global world in different servers. So as you can see, we perform the alignment and registration at the first tier with the global world model update. Then the global world model storage will be done at the second tier. And finally, we will have a data center based architecture in the cloud to handle the long-term storage of the different elements. Also, we need to consider the openness and connection to other meta words, because right now we have, if you remember in the introduction, I talked about metaverses, and this is not good. We should only have a metaverse, a single distributed entity similar to the internet. But already with virtual worlds, it's difficult to interconnect those different metaverses toward one single metaverse. How can we do that with augmented reality? And this is a big problem because a lot of augmented reality experiences have a locality, a physicality. So one of the potential solutions we propose is to replicate the AR metaverse into a virtual world by leveraging the university building information model to provide the base 3D models for this virtual world. As such, despite not having the complete physicality, we can try to replicate as much of the physical environment and the physical event into this virtual world and interconnect it with other real worlds. So in conclusion, in this paper, we studied the feasibility of the AR meta universe at the campus scale. We proposed a client-server architecture that enables client-scale AR when considering campus-specific scenarios where computation-heavy algorithms are required. And finally, we laid the foundations for building our university campus metaverse in the upcoming years. All right, so that was it for my talk, and I welcome any questions from the audience. Are there any questions in the Discord?
Any questions? If no questions, then I have one question.
Mhm.
Yeah. So with this infrastructure you have proposed, so you expect how many students, you know, in a university campus, we need to accommodate student like more than like 3,000 or 4,000 students. As I know, HKUST is a very big university, and also the campus may be split into two. As I know, the campus is HKUST is going to build a new campus. So what do you think the challenge of accommodating students from two campuses and also a big number of students there?
So this is a great question. And indeed, this work was driven by the fact that our university will have soon two campuses. And the idea of this AR metaverse was to be able to bring the two campuses together through virtual elements overlaid over the physical campuses. And this is the entire point of having this distributed architecture, highly distributed architecture, because HKUST has this particularity that we have indeed a lot of students, several thousands of students, and a campus that is geographically fairly small. So we expect to have a lot of students within the same location at a time. And this is why we want to deploy a tiered edge computing infrastructure, ideally with some computing capabilities behind every Wi-Fi access point, so that we don't necessarily support thousands of students at the same time, but a more manageable number of students behind each edge server. Of course, in some environments, like for instance, I gave the example of our university atrium, or the big outdoor environments, we may have hundreds of students at the same time. And this is one of the challenges we will have to tackle to deploy this large-scale campus metaverse. Actually, those large indoor environments are the main challenge because they are difficult to map, difficult to register, and they may have a lot of students at the same time. And this is going to be, yes, one of the major challenges that we will try to address.
Yeah, thank you.
I see there's something in the chat as well. All right, there is a question in the chat as well. I can see.
Yeah, so there is one question in the chat. As for Remindme, could you please explain more about the benefits of an AR Metaverse campus in comparison to only VR, since the environments could change?
So yeah, this is a very good question. And well, this I think is two questions in one. The first part, the benefits of an AR Metaverse campus is to have a physicality in the Metaverse aspects. So we can anchor digital events in the physical world. And as I stated in the applications, this could be very interesting in terms of arts, exhibitions, campus events, and also to support learning, because we can have a metaverse classroom or a metaverse lab that can connect remote students and local students together. And in the case of our university that will soon have 2 campuses, this could connect the 2 campuses together while allowing people to be physically present in the campus. In terms of the environment changing very much, this is one of the major challenges we will have to address. And we are currently working on that to map our university atrium and to address the different changes that may happen in this atrium, because in this atrium we have many student activities and they tend to display banners or sculptures in the atrium that significantly complicate registration. And there are some works already that aim to, that aim to address this problem of moving elements and elements changing over time. And this is what we will continue doing to try to keep this environment registrable despite changes. All right. So I think it's time to move on to the next paper.
Yes. Yeah, so next paper is, let me see. The next paper is a reality check of Metaverse. Our first look at commercial social virtual reality platform, and will be presented by Ruizhi Jiang.
Just a quick word for those of you who present and have not yet sent a your bio. Please send it to either me or Likhang Li, so we can introduce you.
Yeah, actually, we only need one more. Yeah, the paper starting with CWCT. Yeah. And let me do a short introductions for Ruizhi Jiang. I hope I pronounced it correctly. Jiang is a first-year CS PhD student at George Mason University under the supervision of Dr. Bo Han. His or her research focus on mobile immersive computing, networking measurement, and social VR. And he or she is currently conducting a network measurement study of commercial social VR platforms. And he hopes to explore the current stage of metaverse development in the industry and to identify and address design faults in social VR platforms at the network transmission aspects. Now, Jiang, you can start now.
Okay, thank you, Paul. Hello, everyone. I'm Ruizhi Chen. Today, I'm going to present our work, Reality Check of Metaverse, a first look at commercial social virtual reality platforms. This is a joint work with Nanwu, Songqing Chen, and Bo Han. So while the term Metaverse has been coined for 13 years, there is still no unified definition of the Metaverse. In the current stage, with the flourishing of 5G and the immersive computing, the Metaverse is widely considered to be a collection of 3D virtual worlds connected through the internet and the XR. The Metaverse we envision is composed of 4 parts, and they are closely connected to the real world. In general, users with XR devices can access the Metaverse and participate in its various social events. And they can create their own content via 3D modeling to decorate social events in the Metaverse. The content can be traded using non-fungible token through a decentralized blockchain. And the objects in the physical world can also be presented in the metaverse as digital twins that are generated via 3D modeling. So as we can see, the metaverse will be built via multiple technologies, such as 5G, XR, and edge computing. Our research mainly focuses on the network demands of the metaverse. In our paper, we focus on an important component of the metaverse, social VR. Social VR can be considered as a combination of social media and VR systems. In social VR applications, servers need to deliver high-quality social VR content in real time, which might bring huge bandwidth consumptions. Based on our measurement study on several platforms, we conclude the current solutions to this problem in the industry. First, this platform treats the virtual background and the UGC as static content and only transmit the avatar interaction data in real time. Then these platforms all use local rendering approach instead of remote rendering, so that this platform only needs to transmit avatar location information instead of high-quality video streamings. In this paper, we focus on Meta's Horizon Workrooms platform, a social VR platform mainly used for online meetings. Our experiment has two users. One user using the Oculus Quest 2 VR headset and the other user using a PC or a headset. The two users are connected to a different local area networks, and we run Wireshark on the routers of both LANs to capture the packets transmitted between the user and the server. To measure the network impact of each feature of the platform, we only enable and disable the same feature in each experiment. We first explore the network protocols used by Workrooms. Workrooms has two servers. First, the headset user establishes a UDP connection to server 1 and continuously transmits virtual content, while the PC browser user does not establish a connection to server 1 because the PC user only sees a fixed 2D view when accessing Workrooms. Then both the PC user and the headset user then establish connection with the second server using several protocols such as STUN and TCP. And then they transmit multimedia content using RTP and RTCP protocols. In fact, the connection between the user and the server 2 is WebRTC technology, which is a real-time communication technology. Although in this paper, we only focus on Workrooms, in our ongoing work, we measure 5 other social VR platforms. Here, I summarize the network protocol used by these 6 commercial social VR platforms and their capacities. We observed that both UDP and the TCP protocols can be used for initial setup. While after the user enters a social event, the user downloads and renders a static background from the server. And then most platforms use UDP to transfer user interaction data in real time. And in the current stage, all social VR platforms can support more than 15 VR users in the same environment. We then measure the throughput requirements of 6 social VR platforms with 2 Quest 2 users. First, we found that the avatar's motion trajectory does not affect the amount of the data transmitted, which may indicate that these platforms update avatar's location in real time. We also observed that the Meta's social VR platforms have more than 10 times of the throughput compared to other platforms. By exploring further, we speculate that this may be because the Meta's avatar model is more complex than the other platforms. Finally, we observe that the user's uplink and the downlink throughput are symmetric for most platforms when the platform has only 2 Quest 2 users. The essential reason for this phenomenon is the local rendering strategy, which I will explain when I discuss the scalability issues of these platforms. Now let's dive into workrooms. First, we analyze the virtual content flow in workrooms. We determine the content transmitted in this flow by enabling some features related to virtual content, such as changing the virtual background and enabling a virtual whiteboard. We notice that for a Quest 2 user, when another user is a PC user, its uplink does not change significantly, while the downlink drops from 0.6 megabits per second to 0.1 megabits per second, compared to the case when another user is a Quest 2 user. And this 0.5 megabits per second is equal to the uplink of a Quest 2 user. We therefore suspect that the downlink throughput of a Quest 2 user can be divided into the virtual background throughput and the uplink throughput of the Quest 2 users. So we do the experiment where we let 3 other headset users join the room every 15 seconds. We found that the downlink throughput of the user grows linearly with the addition of new headset users by roughly 0.5 megabits per second. This indicates that workrooms face the scalability issue. We also found that the downlink throughput of users does not decrease when there is no other avatars in the user's viewport, which indicates that workrooms does not do any viewport prediction. Instead, it just transmits all 6 DOF data to the user's headset. And in our experiments in other platforms, we found that all current social media platforms face the scalability issues. The essential reason of this problem is the local rendering strategies, that the server only transmits the location information of all other avatars to the user, which leads to a linear increase in users' downlink throughput as new users join. We believe that the scalability issue is one of the urgent problems in building the Metaverse at present. Next, we analyze the multimedia flow of workrooms. This flow uses the WebRTC technology to transfer the audio and the video data. Each user has 2 audio sessions, one for uploading their own audio data and the other for receiving audio data from another user. When a new user joins, the other users will have a new audio session to receive the new user's audio data. And each user also has 2 video sessions, but all video sessions are downlink data. And the number of the video sessions does not increase with the number of increase of new users. Also, we observed that the video data received by the PC user and the headset user are the same because their SSRC field in the RTP packets are the same. The source of the video for the PC user may be the 2D scene it sees, since it doesn't transfer any data with the virtual content server. But the source of the video data to the headset user is unknown. We also observed that the video session 2 has a periodic spike. So we we speculate that this session may be used to probe the available bandwidth. To verify our conjecture, we limited the downlink throughput of a headset user to 1 megabits per second, as shown in the green area in the figure. We observed that session 2 increased its bitrate during the disruption period, which may indicate that it's indeed related to the bandwidth probing. However, it does not help reduce the recovery time of video session 1, which takes about 40 seconds to recover. For comparison, previous work shows that popular video conferencing applications such as Zoom and Google Meet, their bandwidth requirements are similar to workrooms, but they take less than 20 seconds to restore the downlink bitrates after the disruption. Next, we explore some of the advanced features of workrooms. First, Quest 2 user can share a virtual background can share a virtual whiteboard in workrooms, and then users can write on it using the controllers as a pen. We found that workrooms use the virtual content flow to transfer the whiteboard data. So this is one of the evidence we determine this flow is used to transmit the virtual content. And the Quest 2 users can also share their PC screens in the room. We found that the screen sharing features creates a new multimedia flow. Surprisingly, when a Quest 2 user shares the PC screen, the user's original 2 downlink sessions disappeared, but the user's headset screen does not show any anomalies at this time. Therefore, we still cannot know the video source of the headset user. In conclusion, we found that current social VR platforms only transmit avatar interaction data in real time, and they use local rendering approach. However, this approach poses scalability issues. We also observed that there is still a lot of room to optimize the avatar interaction data transmitting. In future work, we plan to explore the network requirements of the social VR platform for different VR headsets. And we plan to propose an open source automated tool that can measure the end-to-end latency of the social VR platform in different geographic locations. And finally, we will explore ways to optimize the data transfer in the social VR systems, such as proposing a viewport adaptive and collaborative rendering social VR system. This is end of my presentation. Thank you for listening. Any questions from the audience?
Yeah, there is one question. What would be an alternative to local rendering that does not have scalability issues?
Oh, yeah, I see. This is a very good question. So the question is, the local rendering will the local rendering approach will pose the scalability issues, because as I described, the local rendering just transmit the avatar's positions to the users. And to address this scalability issue, the best way is to use remote rendering. And because the remote rendering will render, for example, if all avatars are in the same region, the remote rendering technique will render all these avatars into a single frame and transmit the video data to the user. And given that the video resolution will not change, so the data will show linear increase when the server uses the remote rendering. But why current social VR platform doesn't use this approach is that the remote rendering, the bandwidth requirement of remote rendering is very, very high. Taking the cloud gaming application, for example, the cloud gaming is a fully remote rendering system, and it transmits the 2D video to 2D game video to the user. And the current cloud gaming will use larger than 20 megabits per second to transfer the 2D video. And if we use the remote rendering in the social VR platforms, we need to transmit the 3D OF video, such as volumetric video, which the bandwidth requirements will way more large than the 2D video. So in the current network environment, in the current network condition environments, we cannot use the fully remote rendering in the social VR platforms. So I think that's one of the reasons why people always say the 5G and the edge computing are the very important technology in building the metaverse, because it can support the remote rendering technique.
Yeah, and also we have another questions from Tristan. And what would be your recommendations in the design of social VR applications for scaling up to the metaverse usage?
Yeah. So in the network aspect, the first thing I think is to do some viewport prediction. As our experiment in the scalability issues, we found that most of the social VR platforms doesn't do any viewport prediction. And actually the field of view, for example, the Quest 2, the field of view of Quest 2 only 90 degrees. So theoretically, we can save 4 times of data if we do the viewport prediction correctly. So this is the first thing I think we can optimize the data transmission and scaling up to the metaverse. And the second is to use the remote rendering, or at least the collaborative remote rendering, partly put in the local rendering and partly put the remote rendering. So the collaborative rendering is a very widely used in some research paper focusing on the mobile VR system. But I haven't read any paper using the remote rendering in the social AR or VR applications. Yeah.
Yeah, and thank you. So we have limited time. So first, thanks for your inspiring talk. And let's move on to the next talk. Yeah.
Okay, thank you, Paul.
Should I begin?
Yeah, so the next paper is the next paper is extended reality and Internet of Things for hyper-connected metaverse environments. Will be presented by Jie Guan, and he is an MFA candidate in the Digital Future Program at OCAD University and gained an undergraduate degree in digital painting and expanded at the same university. And currently he engaged in extending the metaverse with Internet of Things, and extended reality. Now the stage is yours. Can you share the screen?
Yes.
Yeah.
Okay. Can you see my screen right now? Okay. Hello everyone. Welcome to my presentation. And my presentation is about the extended reality and Internet of Things for hyper-connected metaverse environments. And here is my co-authors, and I am MFA candidate in Digital Future Program at OCAD University. And he is Professor Jay Irizarry, and he is Professor Alexis Morris. And we are based in Toronto, Canada. And here's the overview of our presentation. And we will talk about the motivation, background, and extending metaverse theory, metaverse prototypes, and discussion summary. Now we move to the motivation. And our motivation is about, we want to decide the metaverse for smart spaces. So for now, metaverse is growing rapidly with various activities. So such as we are doing meeting in the metaverse, such as performance in Decentraland, such as art show in the Crystal World Show, also conference and gaming and online class in the metaverse. And we see that metaverse are becoming important. And we are thinking, how can we design a seamless virtual and physical metaverse space? So here is some background about the metaverse evolution. And there are many definitions about the metaverse. And we can see the evolution of the metaverse from Denisia. It is talking about from the text-based virtual world and what we are in of the open source decentralized contribution. And this is what we are thinking in the future. We want to burden the border with the physical world with the metaverse. And the problem we are looking about is the metaverse disconnected. And metaverse interaction have challenges. So here is an HCF data from the Rekimoto. And we see that when the user wearing the VR headset, it brought their vision that cannot see and assess the physical environment. So like we are in the virtual reality. And also the virtual objects and environment in the current metaverse platforms do not connect to the physical agents. So what is this disconnect and how to decide for it? So here is our research summary. Our objective is to theorize about what an extended metaverse means and to create design prototypes that bridge the gap for the metaverse. And here is the 4 dimensions we are looking for, like the metaverse, Internet of Things, as attending metaverse, and the design and prototyping. And our research question is, how can the gap between the metaverse and the physical world be minimized to increase the dynamic engagement for smart environments with mixed reality and Internet of Things? And now we are going to talk about some of the backgrounds. Here is some of the previous research about from our ACE lab of the IoT avatars. And we are prototyping for the SR and IoT interface. And here is a mobile device to connect a physical plant with an AI experiment. And also we have another paper talking about how we use HMD to achieve a more immersive experiment and more adaptive the virtual plant. And also we have different another approach about HoloLens and also computer vision to capture the physical information and visualize the virtual things. And here is the architecture about one of our prototype and about the mixed reality and Internet of Things, about to propose and smart spaces for AI design and prototyping and applicable to multiple scenarios and use case. And also want to implementation of the functionality for future work. And here's some other related example about AI and IoT from Joe and Kim. And here is a shopping experiment about how you can connect to the physical clock with your mobile phone and also control a physical light with an AR in a mobile too. And now I'm talking about the theory about the extended metaverse. And we are thinking how to solve the metaverse disconnect. So on here, we can see like when people using their desktop or phone with the 2D screen to with the metaverse platform, they have some gap to connect to their physical objects. And also when people wearing the VR headset to enter the metaverse, it even also just block their vision, and also they cannot just like see or access information from the real space. And here is what we think about the metaverse. It is disconnect with the real world. And here is the mixed reality agent framework. And it's talking about 3 dimensions about how they decide the mixed realities. It is for the embodiment, agency, and interaction. So we are thinking how we can decide an agent to bridge the gap or extend the metaverse in the real world based on these 3 dimensions. And here is our extended metaverse agent framework. So firstly, we want the user to have an mixed reality head mounting displays, and we want to make the user immersive and depth space. And also we have a metaverse environment with some virtual objects and agents. And also we have the mixed reality environment that the physical agents such as smart lights and also some 3D user interface. And these environments are connected with the Internet of Things. And here is some working in progress framework about more complex detail about how we decide the extended metaverse agent with more detail on the physical space and also the MR space. And we have some prototypes. So here is the first prototype about how we decide the SRI LAN controller. The SRI mean the extended reality and Internet Things. And so we can see on here, it is like current platform of the metaverse, it is have disconnect with this physical space and also this virtual environment. And this is how we try to connect them. And also this is the tool we are using. And here is the video about what the prototype looks like. So first, we have a user wearing a HoloLens, and they can just control the virtual boat. And then when you put the virtual boat inside the lamp, and the physical lamp it is turned on, and the virtual environment is turned off too, and then they can see the physical environment. And then if they just get out, and also the virtual environment come back, and also the physical light is turned off. And the outcome it is like we connected the metaverse and a physical space with a turn on and off light interaction, and they can switch between an immersive metaverse environment and the mixed reality environment. And here is the second prototype we designed for the SI ambient lighting experiment. So we have set out some fillet hill light on the environment, and then we have the user also wearing the HoloLens, and that can control a rocket to touch the virtual planet. And also here is the video about the prototype, like when the user control the rocket and then maybe move to one of the plant, and the physical environment is turned to the color of the plant. And also the outcome of it is like enhance the environment with the ambient light and a mixed reality 3D interface for the physical agents with metaverse objects. And discussion. And for this, where we explore the concept within a need to decide to the extended metaverse. And this work is a proof of concept of how we thinking about the hybrid extended reality and IoT environment. And the vision is remind to generate a stronger connection between the real and virtual space. And the direction for future research maybe include a more detailed evaluation about the effectiveness of attending metaverse agents and a more accessibility attending metaverse solution. Like here's something I am trying to working right now with the Oculus Quest with a more accessible device and enable the MR experiment. And summary. And this work has presented a design perspective on metaverse, highlight the essential need to create an approach that synchronize and connect metaverse more concretely and physical to stimulate user interaction. And this is some of the select reference and more about paper. And thank you for thank you. And is there any questions?
Yeah, I like the demonstration very much. Yeah, so
Thank you.
it is a very interesting talk. And now we have one question again from Tristan. So he also mentioned that you make a great demonstration. And regarding your first application, the light pub, what kind of real life applications can emerge from this?
What I think for a smart home environment can be merged from this. So for example, when maybe we can imagine the future when maybe most people have maybe smart glasses, so they can have a maybe virtual representation about a virtual boat, and maybe they are able to move around MR space and then maybe with the metaverse. So when people want to control the light, so they can maybe, okay, just manipulate the virtual objects that can turn on or turn off their light and even maybe change the color of their light. And also this system maybe can connect to more smart home devices. Maybe for example, maybe like we can have a smart bridge and maybe more, this is what I think, and maybe a smart driving experiment.
Yeah.
Thank you.
So another question is a technical one. How do you register the small physical objects with the virtual objects?
Okay, this is a interesting question. Since I spend a lot of time to just want to solve this problem, and for this project, I just moved them manually inside Unity to anchor the virtual object onto the physical. But what I am research right now, it is like the HoloLens have the QR code that can anchor the virtual objects. And I found that the Oculus Quest 2 also can track and keyboard, and that maybe something can be used for anchor the virtual things onto the physical. Yeah. Horticulture. Thank you. Thank you.
Yeah. So if we don't have questions, then we will move on to the next presentation. And again, thanks for the very great demo. Yeah, and very nice talk. Yeah. Yeah, so the next one is CWCT, an effective vision transformer using improved cross-window self-attention and CNN, will be presented by Man-Xian Li. And I think Li, you can start sharing your screen. Now I try to do a short introduction.
Yes.
For you. And Man-Xian Li is a master degree candidate from Beijing Information Science and Technology University, and she and her research interests are long-tail image recognition and the applications of computer visions. Now the stage is yours. Yeah, and you can go ahead.
Yes. Hello everyone, my name is Mengxin Li, come from Beijing Information Science and Technology University. It's my honor to share our paper CWCT, an effective and transformer using improved cross-window self-attention and CNN in this workshop. And first, let's talk about the relationship between Metaverse and computer vision shot. This is a screenshot in VR chat. In my opinion, this is a game that does it to the fantasy of a Metaverse universe. And to build a world like this, we need some important technology such as 3D reconstruction, motion capture, intro navigation, and computer vision. For example, if we want to quickly rebuild our surroundings to translate a real world to virtual world, just like the picture, we need coordinate information and semantic information. Computer vision will provide semantic information about surrounding targets. When we talk about computer vision, the CNN must not be ignored. In the field of image classification, for many times, the network model based on CNN has achieved better results. The picture shows a classic VGG16 network. It obtains image features by deep convolutions of images. But as we know, the accuracy of early CNN can only be solved by increasing the depth of convolution layer. And increasing the number of layers will cause gradient loss. Of course, since the excellent networkers like ResNet have emerged to avoid this problem. But essentially, the feature that CNN use convolutional network to obtain image features has not changed. In summary, CNN has those disadvantages. The deep layers make the front layer parameters change slowly. The max pooling ignores the connection between the whole and the part, and the SGD makes local optimum. Transformers performance in NLP has been well documented. It has advantages in computational efficiency and can support large models. In computer vision, its view has the ability to get close to the end. The core idea is to divide the image into a sequence and pass it into the transformer in the form of patches. Because the transformer has no local preference, it has better performance on large-scale datasets. And the attention is more interested in classing regions. But the large datasets means more than time. And vision transformer always creates hard model. Meanwhile, many fully connected layers may be cause overfitting. As we can see in the first feature, the parameter scale of vision transformer mentioned at a higher level. The second feature shows a type of work about CNN and transformer. In CMD network, they propose a model named CMD block. In CMD block, they use local precision unit, a lightweight MHSA, inverted rational FFN to get local feature and long-range future. CMD shows the greater potential of combining CNN and transformer because it can reduce model complexity while get high accuracy. Based on CNN and vision transformer, we improved CMT. Based on CMT transformer and improved cross-shaped window self-attention, we present improved image classification framework combining C and transformers, which is called CWCT transformer. CWCT captures local features by using optimized cross-window self-attention mechanism and global features by using conventional neural networks. The CWCT block consists of a local precision unit, a cross-window self-attention model, and an inverted residual feedward network. Every input image will come to CWCT stream, but 3 convolution layers each will transfer to CWCT block. The first model of CWCT is a local precision unit. In this model, the LPU will extract local feature. In visual tasks, the absolute position codes are generally used to represent features in previous transformers because it adds a unique position code to each patch, which easily destroys the transition inverse. In addition, when transformers ignore the local relationship and structural information which within patches, the original field attention has powerful long-distance flexible modeling capabilities. Its computational complexity is closely related to the size of the feature map to extend the attention area and obtain the local repetitive. We use CSV on the straps from a improved cross window. As mentioned about the key point of the cross window self-attention design is to perform line operation before self-attention and the relative position division B, and in the next part, according to the horizontal and vertical directions, mud head is divided into 2 groups into characteristics repetitive fields with different angles. Different gets better performance by changing the local of the shortcut connection from FFN used in VIT. We use IRFFN. The IRFFN composed of a passion layer, a deep wide convolution layer, and a projection layer. Let us analyze the computational cost of standard VIT and the CWCT. The standard transformer block is composed of MHSA and FFN, assuming that the input feature size is n multiplied d. R is a Poisson ratio of FFN. The K and the V are the dimensions of key and value. From the above analysis, we can see that compared with the standard transformer block, the CWCT block has a lower computational cost and it's easier to process feature maps with higher resolution. We have carried out image classification experiments on ImageNet 1000 dataset. We trained the model on the training set and verified accuracy of image classification on the vantage set, including top 5 accuracy and top 5 accuracy. To make a fair comparison with recent work, we adopted the same training strategy and augmentation strategy as DEIT. That is NMW optimizer and 300 epochs were used to train the model. As the table shows, on the ImageNet dataset, the top-one accuracy of CWCT-TI is 0.2%, 7.2, and 9.6 higher than CMTTI, DEITTI, and ResNet 18 respectively. Experiments have proved that the CWCT network introduced by cross-window self-attention has better performance in image classification tasks. To compare with CMT, we use tiny ImageNet, which sets randomly selects 80 categories of image from the ImageNet 1000 datasets. As the table shows, it can be seen from table that the top one accuracy of CWCT-XS is 0.9 higher than that of CMT-XS, and the top one accuracy of CWCT-S is 2.3 higher than that of CMT-S. The model parameters of CWCT-XS is 6.1 lower than that of CMT-XS, and that of CWCT-X is 7 lower than of CMT-S. The model operation speed of CWCT-XS is 0.2 faster than that of CMT-XS, and that of CWCT-S is 0.2 faster than that of CMT-S. Flops and the parameters in the experimental results show that CWCT mode is better than CMT in the complexity and the space complexity. The experimental results show that the training time of CWCT is less than CMT. According to the multiple measurements results of the above experiments, CWCT has better performance than CMT due to its leading achievements in the amount of model parameters and the computational power consumption, both in the training process and in the deployment process. Therefore, CWCT is superior to CMT in the same expansional settings. The conclusions are as follows. First, the combination of CN and transformer can effectively reduce the amount of model parameters and the complexity. Second, cross-window attention can obtain more effective information and improve accuracy. Third, cross-window attention is very helpful to reduce the complexity and reduce the model. Okay, that's all. Thank you for your listening.
All right, thanks for your nice presentation. Does anybody in the audience have questions?
Yes. Okay.
Okay, I have a small question, which is, so that was quite an, oh, there's a question from somebody who was raising hand.
Thank you. I want to know what the difference of the, CBAT. CBAT is one of the neural network. And what the difference about CBAT to CWCT?
I'm so sorry. Could you please come again?
CBAT is a new neural attention framework. It have a, I'm sorry, now CBAT is
could you maybe type in the chat the name of the neural network? I think that may
yes,
help.
Yeah. Then please progress it, and after I'll typing.
Okay, so while the other participant is typing his question, I wanted to ask, so what would be the concrete applications of this research to the metaverse?
Okay. The image recognition is conducive to the construction of virtual world.
Okay, so using that to rebuild virtual worlds, right? I mean, you would use, so this paper could be used to build virtual worlds based on existing images.
Yeah, I think watching like we can get the image and then we can use it in the virtual world. And overall, the paper looks great. Yeah, so we can see a lot of technical details in the paper and as well as the presentation. So again, thanks for your presentation. And due to the time limit, I'm very sorry that we have to move on. So let's do our last paper in these sessions. And I do advertising. If we want, I mean, after finish the next presentation, we will have a coffee break. I'm so sorry that we cannot provide the coffee virtually, but after the coffee break, we will have a panel building the metaverse from diverse perspective. So we invite everyone in this channel to join us and have a very extensive discussion. So the next paper is will be introduced by Tristan. Yeah, so Tristan, yeah.
All right, so the next paper is environmental, user, and social context-aware augmented reality for supporting personal development and change. And it will be presented by Maria Gorlatova. So while she starts, okay, so maybe I introduce quickly. So Dr. Maria Gorlatova is a Nortel Networks Assistant Professor of Electrical and Computer Engineering and Computer Science at Duke University in North Carolina. She received a PhD in Electrical Engineering from Columbia University and her MSc and BSc, summa cum laude, degrees in Electrical Engineering from University of Ottawa, Canada. And Dr. Gorlatova leads the Duke University Intelligent Interactive IoT Lab that develops pervasive distributed sensing and computing platforms to support emerging applications. She is a recipient of multiple awards, including the 2021 NSF Career Award, the 2021 Facebook Faculty Award, the 2011 IEEE Communication Society Award for Advances in Communication, and the 2016 IEEE Communication Society Young Author Best Paper Award. So, Dr. Gorotova, the floor is yours.
Thank you, Tristan. Can you see my slides?
Yes, we can.
This is good. Okay, excellent. All right. Hello, everyone. It's my genuine pleasure to be here to talk about our work. So I'll talk about our work on augmented reality for supporting personal development and change. And this is brought to you by two labs at Duke University in North Carolina, my Intelligent Interactive IoT lab, and Big Ideas lab led by Jesselyn Dunn. So collaboration between EC and BME departments. So a little bit about my lab. I lead the Duke Intelligent Interactive IoT Lab, where our core research direction is to make augmented reality reliable and context aware. And by reliable, we mean reliable so that you would truly trust your life to it, that you would trust it to be a part of surgery that's done on you, or you would trust it to guide you through working with a heavy and potentially dangerous robot. In terms of context awareness, what I mean by this, I'll talk more about it during the presentation. So what we envision using AR for is a set of applications that help the user lead her best life, so-called eudaimonic applications that help users establish healthier habits, pursue professional goals, strengthen emotional regulation skills, or perhaps even combat substance abuse, for instance, quit smoking. And this is broadly related to an area of mobile health that deals with being able to deliver interventions at the right time and interventions that are right for the user. So the formal definition of these types of interventions are, they're called JITI, just-in-time adaptive interventions. And the formal definition is on the screen here, that the interventions are delivered in the moment and they are adapted to user state. So a couple of examples of such interventions delivered via AR interfaces are shown on the screen here. In the center of it, you see an app that detects that the user is getting hungry, and it shows the user a healthy food option. So to get them excited for choosing a healthier option as opposed to something that's less good for them, and also shows where the users would be able to go to get such healthy and exciting food. And to the very right of the screen is an application that helps the user keeps focused on her goals. So for instance, in this case, the user wants to study. So we cover a distracting object in the environment, a mobile phone in this case, with a hologram. And we also present to the user a virtual representation of what it is that she is aiming to achieve. So let's say diploma or herself in a cap and gown to keep her focused on her goals. The idea of just-in-time adaptive interventions isn't new. It has been developed for mobile phones and smartwatches. But with augmented reality, we are really talking about bringing interventions to life, taking them to a completely different level. So with mobile phones and smartwatches, the best you can do is to have a smartwatch beep or to deliver text messages to a mobile phone, for instance. And with AR, we can be talking about immersive, engaging, realistic visualizations. We can vary interventions considerably. With a smartwatch, as the watch continues beeping, the user just starts ignoring it. And with AR, we have the potential to deliver interventions that are significantly varied so that the user does not start dismissing them. The challenge is to deliver these truly adaptive interventions. We need to take context awareness for AR to a different level. We need to make augmented reality aware of environment, user, and social context at a completely different level than it's capable of right now. So, and that's what we are outlining in this paper. Our high-level idea is to develop multi-device architectures where other devices in the environment are supporting AR device in sensing and in computing. So we imagine using wearables and IoT devices to provide additional information about the state of the environment and the state of the user. And we imagine using edge servers to provide additional computing capabilities to help AR devices execute much more complex algorithms or save resources. we have identified three pillars of what it would take to take augmented reality to the next level in terms of context awareness. And they are this integration of multiple devices, use of edge computing to improve the performance of SLAM and scene understanding algorithms, and specific techniques for select areas of context understanding for environmental, user, and social context elements of it. So I'll talk about these pillars in order in the rest of this presentation. So in terms of multi-device integration, it's quite intuitive what wearables and IoT devices could bring to supplement AR's context awareness. We essentially get more information. AR only provides us with, it has very powerful sensing capabilities, but it's only one viewpoint. And in terms of wearables, we can get some idea of user behavior and some biometrics through AR, but there are devices that are much better at capturing heart rate, for instance, or other biosignals. And with IoT, we get additional information about the state of the world around the user. And we also get the persistent information about the state of the world. AR devices only capture where they're pointed to at a given moment. And IoT can give us more. So it's worth noting that the core connectivity between AR, edge computing, and IoT and wearables can be readily established. There are many protocols for it. There are many platforms for it. It's straightforward. Undergrad students can generally do that. But where the challenges arise are that it's one thing to collect data, but the other is how we can translate this collected data to enhance context understanding. This is where a lot of challenges lie. So for instance, let's take the scenario where we have cameras of IoT devices and cameras of AR devices that are capturing the environment. The quality of data that's captured by these two classes of devices will differ over time. So in some instances, for instance, a video that's captured by the AR device will be blurry. And in other cases, the video that's captured by an IoT device will be abstracted. So we need to develop algorithms that deal with this. So we need to develop a set of online metrics of data quality and need to develop higher level algorithms that take these metrics into account when making context decisions. And video is one example, but this is the case for all the other types of algorithms that work across different sources of data, as is envisioned here. The other important part here that still requires quite a bit of work, quite a bit of research, is that in a lot of these cases, the delta we will be capturing is multimodal. So for instance, we will be combining the results of user context awareness that we get through egocentric video, through eye tracking, and through heart rate measurements. And there are a lot of challenges that are associated with developing robust, reliable, multimodal algorithms for cases like this. In SLAM and scene understanding, first of all, in terms of SLAM, modern AR platforms are just absolutely spectacular in how far they have taken SLAM, that we are able to achieve markerless augmented reality in many spaces. So the progress has been absolutely incredible to see. But the limitations are still quite severe, especially on platforms that are slightly lower end. But in general, we are able to place virtual objects in a real environment, but we see many artifacts as well. So for instance, drift, the unintended motion of the holograms that's shown to the left of the screen is very commonly observed. Incorrect scaling of objects that's shown to the right, that is virtual objects being shown as either gigantic or tiny. That's also very common. We've actually done work on that quantified visual artifacts in AR systems in different elements of it, and it's persistent. It's there. So we really need to do better, and we do need to do better in terms of semantic awareness as well, awareness of objects and surfaces in the environment. And this is where edge computing, in my opinion, is the core enabling technology that will take us there. There's a lot of work on using edge computing for different elements of improved scene understanding. Several papers on running deep neural networks for, let's say, object recognition on edge systems. A very interesting recent work on using edge computing to run advanced DNNs for light estimation in AR systems. We ourselves have recently looked at how to improve quality of depth data with DNNs that run on edge servers. And there's very, very interesting work on using SLAM in conjunction with edge computing that taking computationally expensive parts of SLAM pipelines and running them on the edge to reduce resource consumption for AR systems. So I see this as the core for enabling environmental understanding of the future. There's clearly a lot of recent work that explores it. And I believe that in the future, we will see more and more of this, and we require this for the metaverse to truly happen. So now I want to talk about the specific elements of context awareness that we envision for our system: environmental, user, and social context awareness. And for them, I want to start with describing what types of interventions they enable for us, and then talk about the core research challenges in these areas. So when we talk about environmental context awareness, we are talking about enabling interventions that adapt to objects present in the environment or objects that aren't present in the environment. So for instance, in the case that is shown on the screen here, we need to detect that a mobile phone is there so that we are able to cover it with a hologram to not have it distracting the user. The challenge is that in environmental context awareness, there is a huge gap between what we would need for a lot of possible applications and what currently exists. And we will do better with multi-device architectures, and we will do better with edge servers, but we will never be perfect in environmental understanding. And the reason for that is that in both SLAM and machine learning that environmental awareness relies on, in both these areas, there are fundamental robustness issues that aren't even well understood by the theoreticians in the field. So there's a gap in being able to make them robust. So we will never see zero error in these conditions. Never is a strong word, but not in the next 5 years, let's say. So what we believe is the path forward is to borrow internet designers' philosophy and to build reliable applications on top of unreliable underlying technologies. Same as in the internet, we build reliable application layer techniques on top of best effort, transparent, and MAC layer protocols. So for instance, we could adapt our interfaces to the errors that are expected. And there's a lot of very interesting work on it. For example, fuzzifying the borders of objects that we are detecting, since we expect the borders to be imprecise. And the example that's shown on the screen here, that's one of our early work in this direction of developing these types of interfaces. Here, if we detect that we expect a large amount of drift in an area, we show one visualization to the user. We warn them that the hologram would be drifting. And if we do not expect a large amount of drift, then we present them a different visualization and we guide them differently in hologram placement. In terms of user context awareness, this is where we want to know what the user is doing and what the user is experiencing to adapt intervention to them. So as is in the example on the screen, if the user is hungry, we present them a visualization that addresses, that relates to that. And in a lot of work on interventions based on user states, the holy grail is not detecting the state of the user, but actually predicting it. So we do not just know that the user is hungry or that the user is angry. We want to know that the user is about to get hungry or about to get angry. And then we can present them an intervention before they get to a very unpleasant, undesirable state. And we can do that with the types of systems that we envision. We can collect the right amount of information to generate these types of predictions. The issue that arises in user context research is that it is becoming increasingly clear that for a lot of these types of techniques, algorithms that are trained on generic populations really do not do well with individuals. So we need to collect some information that is specific for the user, and we need to develop techniques that allow us to incorporate that data that may be limited into the context awareness algorithm. So the whole area of few-shot learning, we believe will be very important in this space. And then finally, in terms of social context awareness. So for a lot of applications that we would like to build, it is actually very important to know how the user is doing in relation to others. Are they having a good time? Are they engaging in interactions? Are people around them smiling, or are they having a fight? And it's worth noting that this type of information cannot be obtained with traditional technologies such as mobile phones. That there, the best you can do is to get to some kind of encounter profiling that tells you whether people have been in proximity. And with AR and with other supporting platforms, we really can get a very rich understanding of the environment, of the social environment. The challenge lies in this very core consideration of bystander privacy, that by definition here, we want to analyze other people that are next to the user. And this is very tricky in public spaces. So we envision first deploying these types of applications in environments where everyone supports the goals of the user, for instance, at home. And then for deploying them in public spaces, this becomes very challenging and needs additional security and privacy research. So in summary, we have outlined a path towards using AR for good, for fostering positive growth of individuals. We have identified AR as a mechanism for delivering immersive, just-in-time adaptive interventions. And we demonstrated how robust context awareness is a key missing component there. And we have outlined a set of core research directions to take it to the next level. I would like to thank our sponsors, and I'll take questions now.
Thank you for the very instructive presentation. Does anybody have questions in the audience? Well, while they maybe think about their question, I have a small question that is a bit on an extension on what you described. So typically, you described a lot of different problems, including how SLAM tracking can drift or diverge, and how to use multi-device applications to propose interventions to the user. And at the intersection of both of those, this is a problem we have encountered a lot, where when you have very dense deployment of IoT devices, it becomes very difficult to accurately register them. So could this be solved through multi-device solutions, or also with user-centric solutions to kind of adapt to this issue?
Yeah, definitely. I think that's definitely the case. So for a lot of these cases, you want IoT devices registered very well as well, and this is problematic. So definitely there is this is an important area of research, and thinking about that in a cross-platform way would be quite cool to explore for sure.
Thanks. Do we have any question from the audience? Oh, there's one from.
Yeah, there is one from. Yeah.
So thanks for this presentation. In your model, how do you see the presentation of shared collaborative AR elements? Also, would you say you are focused on agent research?
So yeah, so for shared for shared elements, essentially you need you do need all of the same improvements, and so we envision using Edge as a kind of the center for coordinating multiple devices and for enabling some of the some of the shared experiences. So definitely, we see this as an age supported age centric platform where that's how that's done. There's a lot of there are a lot of interesting things that you can think about. That if you are able to have multiple users who all have AR, you can have lots of cool interventions that are geared towards it. So, for instance, if one user is busy and the other user is wearing an AR headset, you can actually warn them about the other user being busy and just tell them to not disturb someone else. So I think that there's a lot of promise in that. Also, the other interesting element of shared experiences is that in this case you get feeds from multiple AR devices and multiple wearable devices. So you should be able to do much better in context detection and especially in user and social context detection, and that should be very interesting to explore. In terms of agent research, could you elaborate more on this?
Yeah. So yeah, I'm just thinking in terms of the idea of, you know, when I'm thinking of let's call it an avatar of an object or a hybrid mixed reality IoT object. You know, those objects can kind of do things on behalf of the user. So on the one hand, you're presenting content, right? To say, okay, you know, you should be having lunch, right? But then the notion of what happens when you tie in something like a Google Assistant, right? Or an Alexa or a Siri, and so you have questions of the entire system becoming itself a bit of an agent character. So developing its own or designing it such that it seems like it has a degree of agency. And a way to almost have a history of its ability to interact with the user and even have goals of its own, you know. So there's a whole set of theory there.
Yeah, no, we did not explore that yet, but that's very interesting. So we're mainly focusing currently on improving context detection here, but that sounds like a very fun direction.
Yeah, I think it's quite interesting. But let me just say, I definitely enjoyed your presentation.
Thank you.
It gave me a lot of things to think about. Yeah.
All right, so thank you. I think we need to keep on time because we're almost on time. So might as well try to keep it that way. All right, so moving on, as I stated before, we have a best paper award that we decided to give because, well, we were actually quite amazed. The program committee was quite amazed by the quality of the papers and the submissions we got in this workshop. So for our first iteration, this is honestly the best we could imagine. And there was one paper that really stood out in terms of both the thoroughness of the study, but also the applications. And this is the paper from Ruiji Sheng, Nan Wu, Songking Chen, and Bohan called Reality Check of the Metaverse, a first look at commercial social virtual reality platforms. And the reason why we decided to give the best paper award to this paper is, first of all, because the study was very thorough and detailed the network aspects of several current virtual reality platforms. And through that, they actually raised many significant issues at network level that will likely impede the development of the metaverse. So especially for VR-based metaverse. And so not only that topic was timely, but it also presented very concrete application and that we believe should drive the immediate technical development of the metaverse. So for these reasons, we give them the best paper award. So congratulations. And we will send you a certificate a bit later by email, I guess. So thank you very much.
Yeah, thank you. Thank you. Thank you, Dr. Lee and Dr. Brand. And also thanks all the paper authors and the participants. I learned a lot from your work and the discussions tonight.
Yes, this is something I want to emphasize, which is it was a difficult choice because we had very, very good papers overall and very good quality. So thanks also to everybody else that contributed to this workshop. All right, so now let us take a, let's say 10 minutes break because I need a coffee before the panel. And so after that, we will have a panel entitled Developing the Metaverse from Different Perspectives that will be moderated by Dr. Peng-Yuan Zhou. And we invite the audience and especially also the authors of the papers that were presented today to stay and actively participate in this panel, because it's always more interesting when you have external contributions and discussions. All right, so let's meet again at, so New Zealand time should be around 4:05 p.m. Then we can start the panel. All right.
Okay, guys, I think we can start right now the panel. Yeah, so there are a lot of questions regarding metaverse in general, especially VR, AR, and MR. So my plan is to throw some like common questions that concerned by the society, and we can have a quite relaxed discussion. There's no like speaker order or whatsoever. We have a few invited panel participators from our own network, of course. But again, all the audience here, you are very welcome to freely speak right away. So yeah. Okay. The most frequently question I personally got is the hardware limitation. I think all of you have met with this more or less at some point, especially for VR and AR, since they require a lot of data transmission and is computational intensive and latency sensitive. So we have been feeling this hardware development is kind of like slowing down the whole ecosystem because everything built upon it has to rely on development of the hardware. So how do you guys think what's the biggest limitation we got from hardware perspective, and how we may work around the hardware limitation by some maybe networking or visual CV techniques to kind of fade out this limitation to make the users transparent to how develop the hardware limit or state of the art performance. Yeah. So anyone want to talk first about hardware limitation? Don't be shy.
Opinion. I think maybe we can invite, some of them, the audience or other participants, that to turn on the camera if it's convenient. So then we, the people feel more interactions over there, right? So
yeah, good point. Yeah, guys. So if you don't mind, please turn up your camera. Let's make it feel more real, even though we are connected remotely.
It's very easy. Yeah, it makes sense. Because people are from different regions, and maybe some of them are in the evening, some of them are in the morning. So it may be difficult to ask everyone to turn on camera, but it is convenient, right? So maybe we just turn on camera, and then you can have a discussion more friendly, more real. Yeah.
Yes. Okay, I see a few people opened up their camera. This actually might become a serious issue when Metaverse is widely deployed. So everyone use their avatar to represent themselves, and we can't see their real faces. So yeah.
That would actually help for the bunch of us who are currently working from home, actually, and don't want the surroundings to be too visible. Okay. Yeah,
right.
I see people are open.
Yeah. Okay. So actually, I'm in the office. So I've been, most of us actually, like me, Tristan, and I think, we are in Hong Kong. So it's pretty hot today here. So we have like 25 degrees in Hong Kong now. It's like a little bit like the summer. So it's 25 degrees. But I can guess that, maybe New Zealand is also at the end of this summer, I guess. Okay, so Pengya, maybe so now we got more people turn on camera, and I guess that you can repeat again your questions, and then maybe we can get someone to start with saying something, right? Maybe I think Tristan can share his idea first, maybe.
Yeah, sure. Okay, thank you. So yeah, since all of us probably coming from different specific fields, subfields in this metaverse umbrella. So I will just bring up some very general high-level questions so that most of us can participate in the discussion. As I was mentioning, the hardware limitation is a big one for everyone because it kind of slow down the development of our techniques. So how do you, what kind of hardware limitation have you been feeling in your research work? And do you have any like related proposals or ideas how we can work around the hardware limitations by maybe software techniques? Yeah, maybe Tristan, if you can start up because you have the DIOS, maybe feasible for this kind of solution, or anyone else, please free to speak up.
Make a comment.
Yeah.
Hey, I'm David White from New Zealand, Auckland. Yeah, I think that the hardware is amazing actually right now today, and like this field of computing is always limited by performance of current hardware, but that's life, and you just got to get on with it. And I think that the thing is the limitation is imagination rather than hardware. Yeah, and time to fulfill that imagination, resources. Yeah, so.
Yeah, good point, David. Yeah, that's true. It's the life we have to deal with. Yeah. So I do see a lot of like hardware startups in recent years, but most of them are like doing kind of repetition of what HoloLens or other similar big companies already done. So maybe they're just developing similar tools, but with a lower expense. So that's the trend what I have seen in the hardware development scenario. Haven't observed like any real breakthrough that can level up the performance we can get from hardware perspective. Like you can see in all these kind of workshops and conferences, even the top conferences, most of them are still from software development perspective. So yeah, like you said, maybe we just have to live with it. Yeah. So,
So
any other? Yeah.
So this it's an interesting way to kind of start this conversation. So I'm Alexis Morris from OCAD University, and I've been waiting for a really long time for the perfect smart glass, right? Really nice field of view, the ability to project content into your space, right? That surrounding like environmental sensing and all of that interesting things. And I think we're on the edge of it. I think it's about to arrive. But while we're waiting for that, the level of disappointment that I've had with some of that, it's not disappointment, but every year I'm like, this is the year, right? When we get the really good smart glasses. I mean, I'm wearing like the Focals smart glass, but if I just wanted to see someone, do a Twitter post or something, that was functional before Google bought the company. But what I've found in research that works well is video see-through approaches, because the video see-through approaches give you really good levels of presence, and we just have to acknowledge that VR is just ahead of AR right now, and so hopefully in the next year to 2 years we're going to really be like able to kind of see our visions happen.
Yeah, yes, Alex. Yeah, same feeling here. Every year, I also feel we are on the edge just to break through and waiting for the announcement from Apple and Google, and kind of like a little bit disappointment after the announcement. So yeah, let's hope we can get through that very soon. Okay. Any others on this point?
Yeah. Hi. So I would like to add to what actually the two previous participants said, which is, oh, that's super cool. We have a metaverse classroom now. So yeah, I would like to add to what the two previous participants just said. That is, I also have this feeling that next year is the year, but I don't only have it on AR, actually. I have it on every field of computing. And I think this is something that we will have, like typically you take video games. Next year is going to be the year we have photorealistic graphics, and we still don't. And how many times did we hear, oh yeah, it cannot get any better than that when a new game is released, and then it gets better. And I think this is something that in terms of hardware, we will always be limited by hardware because we're always thinking one step ahead. When Google Glass appeared about 10 years ago, we started to think it was like, yeah, just a heads-up display where you could indeed display a tweet, and that was basically it. And at that moment, we thought, oh, then we started to think about actually mobile in situ AR. Now that we have that on smartphones, now we're thinking, oh yeah, now we can have this on the portable headset. And then when we have it on a portable headset, most likely we will think, oh yeah, and how about context awareness? Like very pervasive context awareness. And at every time we will be limited by the hardware anyway, and it is up to us to get this development of ideas in parallel to the hardware so that things get built one after the other.
Yeah, I think so. Yeah, it's always like a shifting back and forward between disappointment and the sudden happiness after the breakthrough. Yeah, for all kinds of science, I guess so. Yeah, but one issue I have seen is that so I have this request, ask for opinions or suggestions from governmental or big companies, that who wasn't quite involved in Metaverse before, but after Facebook changed their name, everyone suddenly want to get a hand onto it. So the most frequent question I get is that whether it's very risky to get into the development of hardware, because normally it costs a lot comparing with software, and then the chance of successful is quite low compared with software development. So that's result in kind of like monopoly of, even in current stage, only the high companies like Facebook, Google, Microsoft, they have this courage and budgets and people to invest into hardware development, which may not be a very good thing, because if more people can join it, so I guess it will somehow accelerate the process. But I can understand their concern. So yeah, okay, cool. Thank you, guys. I think we can move on to the next question, which I just brought up actually, is the decentralization vs centralization development of Metaverse. So this concern is always there, and now because of the DAO community, for instance, built on which is the famous Decentraland. So there is a trend and kind of like hope that especially us from researcher academia perspective, we want to push this decentralized trend into Metaverse so that it won't happen again like a traditional social network. Only a few top companies control all the markets, and we have to live with it. So, but I have used Decentraland for a few times, and I haven't seen. I mean, it's developing. It's getting slightly better now and then, but we can see it has a huge issue of low audience adoption because they lack of big budget to invest. So even though there are a relative big number of small developed multiverses posted there, but the performance there is not quite good, to be honest. So after new users trying for a little bit while, then you got stuck, and then the user just back off. So how can we deal with this? How can we promote decentralization mindset in Metaverse? How can we deal with the challenges faced by the individual small companies that can't compare with the big companies in terms of user adoption and performance improvement. I want to hear suggestions from that perspective. Yeah. Anyone interested in decentralization?
I can say
Yeah.
okay. I just feel like when we doing decentralization in the metaverse, the process is really slow. So for example, like I engage in the decentralized community since 2019 or 2018. What they say they want to just like have a VR platform, maybe almost 3-4 years ago, but now we don't see it happen. And I think just last week or 2 weeks ago, they just released the desktop version about the decentralized. So I feel sometimes the development process really slow in a decentralized platform. So sometimes some people the user maybe lose their patience to waiting for this, and they will lose a lot of users. I feel sometimes, and also maybe like some of the communities in the decentralized, for example, like I engage in the Chinese community of the Dragon City, and it has been developed for 2 to 3 years. Although they host many good events, but it's still really hard to just get the people together. Since like one of the land, it is I feel it's really expensive for a person to hold in a land. But if you are entering a platform, you cannot hold in a land while you want to enter there. So I feel sometimes it's confused. So this is what I think about a decentralized platform. Yeah.
Yeah. Yeah. Good point. Yeah. Anyone else? Otherwise,
yeah.
Yeah.
So kind of along those lines, I was recently, so there was another kind of open web oriented VR space. You may have heard of it. It's called Janus, Janus VR. And well, now they're Janus XR. But what was interesting there is that they were trying to build as if it was a hyperlink based ecosystem, where basically it's a number of different WebXR world spaces that you can just link to within the browser, but also within, like a Mozilla Hubs type thing, or with your VR headset. But what was nice with that was the fact that you can just use it on any platform. Like you could go to their website now and just be able to jump into that scenario. I think there's still a lot of there's just so many sub questions there about not only is because there's going to be a lot of different clusters that form out in this space, right? So there's each of us is doing some research in this space, but for example, we would all go off and build like a separate platform, right? Like a separate architecture. So without some kind of a coalition to kind of to set some kind of underlying framework in place, it's very hard to kind of stay on the same page with the different decentralized goals and things like that. But I have hope that that we can build on top of the existing decentralization of the internet, things like blockchain and whatnot. I agree with what Maria Gorlatova had mentioned in the last talk about how we need to kind of accept that let's build on top of what we already have, and so that's an interesting motivation that's there, because we know the current internet, it works, right? Works really well. So now how do we get that into the next step?
Great. Yeah, maybe I also yeah. Sorry, Pingyang, you continue.
Please.
Okay, so yeah, maybe I'll come in to just refer to Alex's comment idea. Right? So basically, yeah, I also see that good that you mentioned about blockchain. So I have seen actually the building decentralized thing is pretty difficult. Even today, the people talk all these Web3 people, right? They talk about Web3, talk about building decentralized thing, but it seems clearly most of this platform they mentioned, when you talk about platform, we're talking about something centralized, right? So when so even these Web3 people, they talk about this, building things decentralized, but then you see that, actually, even OpenSea, right? Some of this NFT platform, they're all kind of platform based, right? So, it's kind of, the idea is very nice, but when you implement, you'll be able to choose some, digital wallet, right? But, you can only choose from 3 digital wallet, and then all these are run by some company, right? And then when you host, you're going to host your content on some, NFT, right? Then actually this content distributed, some of these file system actually are running by another platform. So, it kind of, you can see maybe it's at the beginning, but I can see that it's pretty challenging. You want to build things very decentralized, in the future for the metaverse.
Yeah, probably that's the case.
Yeah, and I think we really do have to draw inspiration from things that we know work, for decentralized systems.
Yeah.
Like,
so I think, for example, can we just consider decentralized and decentralized work together? Just like maybe decentralized, it is a node and something they can be construct a platform of centralized and decentralized together. I think this maybe can, I don't know.
Yeah, and another thought there about that is, so just similar to what Jill is mentioning, is that we need all of the activity that's going on, right? So all the activity that's going on in enterprise, right, is actually pushing everything forward as well as what we're doing in academia. So we need more bridges, I guess, and that's probably going to be something that's really important. For example, I mean, Facebook gets a lot of Meta gets a lot of interesting comments and whatnot, but I do think that they're definitely pushing the ecosystem forward in a substantial way. So being able to kind of build and map into all these different ecosystems is very important. But to kind of do it in a way where you can kind of merge, these platforms that are completely separate. Yeah, it's a very challenging research question.
Yeah, I guess so. Yeah, okay, let's move on, because the time is limited. So yeah, how about user experience? That's maybe the top thing for VR, AR, and all the Rs, since we are stressing on the immersive experience sold by Metaverse. So how, maybe from content creation perspective, HCI interaction perspective, how can we improve? What can we do? And what's still lacking there? Yeah.
Yeah, maybe I start with this topic regarding the user-centric aspects for the for building the metaverse. Nowadays we what we mentioned in the talk, or maybe someone read the survey we have written in last year October. We mentioned one very important aspect is the sense of presence. How can nowadays the smart glasses, they can only provide visual feedback, or they can only provide the audio feedback. So beyond this, what is the aspect we can improve? I think a lot of people are mentioning haptics. Can we feel the objects remotely? We have the digital overlays, but we cannot touch it. It is very different from what we have on the desktop. On the desktop, you can still feel the you can still touch something, at least the keyboard and the mouse, but in the digital overlays, it is beyond this level. So how we can design everyday objects and we can have a sense of virtual presence, I think that will be a very important.
Yeah, Can I have a comment here? Yes, actually, this comments was something that I faced with when I talk with users, not the experts of IT experts, that they don't feel the objects and they can't touch it. This is a hardware challenge that that your first question was about that, and this is really needs that we need more tangible inputs that are general, like gloves that can be a general tool, not specific haptic devices, because we can, for a metaverse application, we have lots of many users. So it should be something that is general for many applications for a user. He or she can't buy one device for each application or many devices for each application to just interact with virtual objects. Also, one thing that I get from users when I show them AR or VR application, they say that we can do it in 2D traditional devices like PC, and the value of the immersive technologies is not very obvious for them. You know, they say, okay, that's cool, but is it just a fancy thing, or is it something that has a great value behind it? You know, I think it's a really big question for me.
Yeah, I agree. And actually, our team, I mean, my collaborators and I try to address this aspect. And also, we see other issues like maybe the networking problem can bring some bad user experience. I think some networking people here can also share some of the user-centric aspects for these questions.
Yeah, that's actually something. Oh, go ahead.
Yeah, no, I think one of the core issues for engineering the metaverse is that we have very few metrics, online metrics of user experience currently. So we don't really have much to optimize for from a more networking perspective. So how do you actually quantify someone's experience with an AR platform, for instance? How can we what is it that we can get from it to even tailor the experience? It's really an open question at this point. And then there's interesting work that's starting to be done on it, but it's a wide open area of work, in my opinion.
I have been actually working on that with actually Paul as well, and this is quite interesting because there is no framework to do that. And at the end of the day, most of the works you can do on user-centric aspects of system design in general, and I would not even say network, but like just hardware limitations, software limitation, and all of those things, they're very application specific at the end of the day. But this is something that I think goes back to what I think Vahid was saying, which is there is no real, a lot of people think it's gadgety and there's no real value in those immersive technology aspects. And this probably comes from the fact that we are limited by technology, but we're not entirely sure how to make it nice for the user. So from typically network latency that will cause a ton of troubles, or also I take another example, which is, let's be honest, 95% of VR applications look terrible. They're not immersive. They're made with cubes and balls and spheres. And I think there is a strong aspect that beyond human-computer interaction, there is also the real need to introduce artists in the space, to have aspects that come from not only system design, but also experience design, whether it is from game design or even cinematography. So that's something I think Jake can maybe talk a bit about.
Thank you. Hello, I'm Jake. I'm from Hong Kong UST. So yeah, in terms of the content creation, totally agree with Tristan. So something that I have seen from the VR content creation that probably something not that be focused is about the to me is like the user experience to the creator. So technically, when we want to create some kind of the content, we want a pretty good effect. The one of the things we usually think is very important is the first thing, like a creator needs to be very engaged. So it means that the sense of the presence need to be considered highly to see like how like the creator can get this information and then convey the information to the audience. So I think like the creator experience could be very important topic in this like a content creation process. And one of the limitation, like Tristan also mentioned, is I think like the also related to previous question is also because of the limitation of the hardware. So it kind of create some like limitation for creator for generate some kind of content in the virtual production, and then it will also affect the quality of the products we produce. Yeah, so that's some of my random thoughts. Yeah.
Yeah.
I'm Sonny, and I want to mention about graphics resolution is improved because Metaverse has a lot of model is selling, and perhaps we hope hardware position. We need a good software like as a Unity to appropriate many type of haptic device, I hope. And I think 20 years later, Elon Musk developed brain human interface, then visual and haptic is also integrated, I hope. Thank you.
Yeah, hope so. Yeah, I think a lot of people like us from previously other fields have same concerns with Maria, that we kind of feel like Metaverse or in general VR AR, they don't have a, how to say, quantifiable specific metrics that we can be 100% sure. For instance, we do networking environment, we can do cache hit ratio or networking environment using like loss ratio that can be, for sure, this is like how we can calculate it with math equations. But for Metaverse, since it's more user centric and everyone has a different perspective and feeling, so it's very hard or even impossible to have a standard commonly used, well acknowledged, universal metric system to measure everyone. Maybe that's the thing for Metaverse. So maybe we just can't use other engineering perspective and method to bring into Metaverse. Maybe like Tristan said, we have to, or maybe we should invite artists to include their mindset, like giving scores from their perspective, how this system work. And also, like we have seen a lot from the related papers using user study to kind of do this interactive scoring system. I know that it may be hard for us from other fields to kind of like totally get on board of this, because when we do math equation based metric measurement and comparing that with the user study, it's like not very serious from our perspectives. But I think that's the thing. That's just the thing of Metaverse, and we have to get along with it. And maybe in the future, when the hardware developed to a higher level, there can be some kind of universal measurement of even user-centric feeling. Maybe using like BCI, those kind of biological stuff. But now I think there's still a gap So I think that's the current situation for metaverse environment, and in general, yeah.
Yeah. So I also want to kind of chime in on this point. I think it's really important, to kind of remain or to try very hard to stay on top of what the wave is in this area in terms of on the user experience side. So, for example, right now we know that there's a ton of interesting VR experiences that are being constantly put out there, and what's interesting about that is the shift from 2D related interfaces, 2D metaphors, right, windows and whatnot, to 3D metaphors and the placement of content anchored into the real world and how you would interact with that. So on the VR side, a lot of the problems are I guess we can say they're kind of easier to some extent on the interaction side, because there's complete control over the environment and whatnot. So I actually am very encouraged by some of what I'm seeing on the interface design front related to what some of the VR displays are showing. Now, on the other side to that, so what are some of the more so how can we get to a point where we're like close to what, let's say, an iPhone can do in terms of its interaction, right? And how do we surpass something like an iPhone device on the interaction front? The promising thing is that in the on the XR side, the dimensions of interaction are just way more, right? So we have more than just a 2D display with a tactile, finger input type of a channel. So I think that even right now, we're close to what I think we'll see this surpass the current interaction space. Now, on the art and design and creation side, I definitely think that being able to encourage more, let's call them creative technologists, to kind of to get access to the particular types of tools like Unity 3D that allow for quickly jumping in and iterating on something and seeing it in a head-mounted display, right? It really does change change someone's perspective on what can be achieved in the VR AR medium. Now, for the other aspects of the metaverse, right? Because it's all sorts of stuff, right? Like what is the 3D user experience of doing a Bitcoin transaction, right? The transaction on the blockchain, or something like that, right? I mean, there's a ton of different opportunities there. We haven't even begun to talk about what it means to like take a physical object and manipulate that object as a form of interaction. So there's rich HCI questions there as well.
Yeah, good point. Yeah, I agree. Transforming from 2D to 3D, and there seems to be a whole bunch of systematic and metrics and the measurement perspective we need to redefine. So yeah, probably based on the experience we get from real life. But yeah, how to do that, we don't know yet. So maybe as in a short summary for everyone, maybe we just reach out to the artist and designer and build some collaborations with them and leave that part to them. Yeah, okay. So next, I hope there are people from industry field in the audience. So could you give some experience or takeaway, lesson learned from industrial perspective? Wen Xiao, are you there?
Hello, can you hear me?
Yeah.
Yes.
Hello?
Yeah, yes.
Okay. Okay, my connection is not so good, so I prefer not to turn on the webcam. I'm Wen Xiao from Huawei, and now doing some research in Huawei, and the area is related to AR, VR, and cloud rendering. So yeah, about the last question, we are talking about content creation for the applications, and I think it's not only the artist's issue, it's also the developers. We also need to concern about this. Like for if like let's take an example. If you want to develop your own web page, you don't write every HTML from scratch. Instead, you can just download some HTML template, and you just put all the words and all the pictures you want to show, and then the template will automatically have all the CSS and even JavaScript running. But for now, for the for the aspect of Metaverse applications, or let's say 3D applications, it's not the case. We don't have so convenient framework like
Hello. I think we lost.
him. Yeah.
Okay. Okay. But anyone else?
We already got some very useful insights from the interview. So we can continue the discussion based on what he mentioned. Yeah.
I think he's back. Maybe. Hello. But
hello.
Yeah.
Hello.
Yeah.
Yeah. Okay. The connection is not so stable. Yeah. I mean, we need some 3D UI framework for application development. Like now, if you look at Microsoft, since it's developing HoloLens, and it has a 3D framework or user interaction framework called MRTK, Mixed Reality Toolkit. And about other companies, there's not so many similar things. So, and if you want to develop with MRTK, then your application, at least the UI part, looks like a 3D windows. That's quite weird. So we need more templates, or let's say more 3D UI framework for the application development. Can you still hear me?
Yeah. Okay. Now.
Okay. Yeah. And,
yeah.
Okay. And another aspect is about the so we are talking about industrial perspective. So I think like big companies, they have much more advantages in terms of having a successful Metaverse application. Like Meta or previous Facebook, it can easily turn their 2D based applications into a 3D Metaverse application. And like Zoom, now we are having conference in Zoom, and Zoom can easily turn the interface into a 3D interface. And like maybe some other companies, those social media companies, they have very good chance here. So it's a problem for us to say what's the chances of those startups. And personally, I don't have a good idea here. Yeah.
What about Huawei? What Huawei is doing?
Huawei has its AR multi-user AR platform. Like it's a 3D AR map. So if you visit a street or visit a scenery or visit a mall, then you can have a huge 3D precise map, and then you can we got some AR applications to do the shopping introduction, and to guide you to the right place, and to show some advertisement. This kind of functionalities, yeah, it's working. but only in a limited in a few limited places, because you need to build those maps and it takes lots of efforts.
Oh, excuse
Yeah.
me.
Okay.
Does Huawei provide AR or VR hardware?
Yeah, we have a VR glass, so it's just a VR glass.
I see. It's HMD or a kind of a single product.
It's not a all-in-one equipment. The VR glass, we call it VR glass. We don't call it VR headset because it's quite thin and there is no processing and battery inside. So you need to connect to your phone or your computer via HDMI or USB-C cable. Yeah.
I see. Thank you.
I saw this Huawei VR essay. It looked pretty actually nice. But I think the only we are trying to got this, but then the only drawback I can see is that you have to connect to a Huawei phone, which is you need to be paired up with a Huawei device or maybe a laptop, right? That actually there are some kind of constraint in this aspect, but it looked pretty nice, and also it's not expensive. I think it's like about 200 or 250 euro or something like that. I guess. But I'm not working Huawei.
Yeah, that price is okay. Yeah. But maybe Wenxiao can suggest Huawei to lower down a little bit of their phone's price. It's getting higher. Yeah. Okay.
I don't have that power.
Okay. Okay. Yeah. Okay. Maybe we can move on. I think judging from time left, we have a quota for one question at most. So since the pandemic began, I think it is already 2 years. Yeah, 2 years or so. So a lot of us have been experiencing, especially for those working in universities, this kind of from local teaching to remote teaching that are using Zoom or other similar tools to teach courses. And like we are seeing now, this Zoom, although it has a kind of classroom appearance, but there sometimes it stutter and blurs. So how do you think in the near future, Metaverse probably have a chance to improve this kind of remote teaching in general or education in general, regarding the efficiency, that to cut down the communication cost so that we don't have to travel a lot. We just log in and then start right away the global meeting and teaching. And how can we improve from not only software, maybe also different accessories like the VR glasses you guys mentioned. How do we expect Metaverse to transform education? Yeah. Any opinions?
Yeah. I actually think that's a really interesting scenario. It just so happens in January, I just had the first try of trying to teach this subject to a class in a short-term metaverse theory and practice type course. And I was trying to actually use the Facebook Horizons workrooms to try to see if I can get as many people into that space. It actually felt really, the presence level was there, but the challenge was that, well, not everyone had access to a headset. So you ended up having this scenario where someone is trying to just log in using a laptop, and they don't get any of the benefits of the presence that's there. The designs don't, the two platforms are just so dramatically different. The conventional scenario that we have right now, and what happens if we're in a shared 3D environment. and it having a way to kind of deal with that midterm transition is one of the challenges. But I do see that with I believe that right now Meta is selling tons of Oculus Quest 2s now at a reasonable price, and I think we're only going to see more of that. So the adoption rate is going to go up. This is another case of maybe next year is the year, but I think we're just in a weird interim period where we have to kind of expect to have this fragmentation of VR, AR equipment, and the vast majority of people not necessarily having access. So that's a pretty big design challenge. So especially for those that are actually designing software for that and for that experience, because then the other side of that is you're wearing like something that's separating you from your audience, right? Even if they're seeing like your avatar or something like that, you still have a lot of kind of a disconnect that's kind of there. But it is an exciting thing to kind of experiment with, and I do think that by the time we hit the end of this decade, that's going to be the way that we do a lot of things.
I'm really believe that that metaverse, or I mean that remote education or remote working is really helpful, and people will use it a lot. When I'm not very a fan of virtual reality, but I'm a fan of mixed reality or AR, because you can engage with the environment at the same time, so it can be more acceptable from the users. So I really prefer if we could have a new AR or mixed reality environment that we are around the table and talk with each other or with our supervisor, which we do right now by Zoom. But it can be, why not in Metaverse, or I mean AR environment? It has also, there was a article that says people prefer to watch movies through the Unreal glasses, which is a lightweight AR glasses, and they can, they have more flexibility than common monitors. So I think there are lots of advantages in Metaverse in comparison with this kind of pieces or the smartphones. And then the other advantage that you said, that you don't need to travel, you can be more flexible in your location, and all of them, I feel a bright future for Metaverse.
Very good. Yeah. Also probably also carbon neutral, and
Yeah.
no emissions.
Exactly. Yeah. Cool.
Yeah.
I
also try to so it's very good. I told you also ask Alice about his experience of this. So how many people you were able to put into a VR room, and also how many students actually how long they can wear this headset until feel a bit uncomfortable or dizzy or something. Yeah. So it's
Yeah. So just to kind of answer that, this was the first time that I tried it, and the experience was actually, only 2 people could actually try the actual in VR experience, and then I had everybody else, like another 20 students or so, that are just like heads on a wall, right, using the 2D experience. And so for being in the immersive experience, it was great for me. I could see my slides on the wall, and it was perfect. But the separation of the experience was unfortunate. Was a shaky start. I do have big plans to try to make a lot more of my research in this type of a way, almost like what they call dog fooding in the industry world, where you just go in and you try to build and live in that space. So yeah, so that first class just showed us that there are a lot of interesting problems there, but we really are just waiting on hardware. I think we need that hardware wave. Go ahead, G.
Well, I think for the aware of the physical space when you are in the VR, just get a keyboard like this, so you can just have your keyboard when you're wearing the VR. So I think this can improve a lot of for you to aware the physical space when you use it to interact with the virtual presentation, or maybe you want to control the virtual space, and you can just type the text with the keyboard, and then I think it helped a lot for the interaction in the like the horizontal space.
Yeah, it's a good question in terms of perspective and being able to situate your 3D space with somebody else's 3D space. And yeah, there's a lot of interesting design elements.
Yeah, exactly.
I want observing headset, student observing headset and blinking time or 3P or concentration observing function. Would you develop?
Oh yeah, in that situation, I don't really have a good answer, right? Because the testing was so fragmented that you know, for the student that was in that the students in that scenario, right? So they could see me as an avatar, and I could see them as an avatar. So you can look up Meta's Horizon workrooms to kind of see what that experience looks like. G and I have actually tried this for lab meetings, which was kind of an interesting kind of experience. And I think we need to do a lot more of that. But we need more platforms like this. So yeah.
Yeah.
I think it was really cool. I can feel you are just next to me when I in the VR, so I can hear you some. I am feeling you are just sitting there.
Yeah. Okay. Yeah. Thank you, guys. Sorry to interrupt, but due to time limitation, I think we are very close to the ending. And thank you all for the insightful discussions, questions, opinions, and I think we have a very good atmosphere here gathering. So it very likely we'll again next year host another similar event, probably workshop or conference collectively with another. So if you view, my colleagues have already sent a Google Doc in the chat. If you want to receive notifications for future events or collaborations, probably you can fill in there your contact email or whatever you want us to reach out, or you want to reach out to us. So feel free to fill that form. And yeah, thanks again for all you guys. And I think now Professor Panhui will give a short summary and conclusion. Yeah, Pep.
Thanks, Ping. So thanks everyone. Actually, I'm not really doing so much as summary. So I just want to thank everyone's contribution to the papers, the program, to participation, and also the panel. Actually, we didn't expect we will have a very interactive panel today. So it was very good that everybody jump in, answer questions, and very good discussions. So I think this is really great panel, and I really appreciate everyone's effort. So yeah, as Peng said, we have the Google Doc that we welcome you to add your name. So we kind of definitely would run another workshop next year. So probably we'll get this year was kind of not much time for preparation. So but we can start planning for next year, and we want to get also your involvement, and probably some more senior person. We like to invite everyone to be on the program committee, and then the student will also welcome to you to contribute to the papers, and in different aspects. So it's yeah, thanks a lot. And I also yeah, so it's very nice workshop, and yeah, I think Maria also proposed that we can have a workshop in the ISMA, so we can also look into this case as well. So ISMA is, I think, yeah. So the timing actually, it probably also possible to run two workshops, one in ISMA and one in VR, and get also the AR people to or mixed reality people to also get involved in this in this workshop series, right? So it's very good suggestion. So it's good to get all the input. And I also kind of advertise a little bit that we are now me and Tristan and we are from also Jay here. We're from the Hong Kong University of Science and Technology. So we are building actually a new campus, actually almost finishing in the Guangzhou. So it's very close to Hong Kong by high-speed train, like 40 minutes by high-speed train. So we have this new department called computational media and art, right? So we are recruiting people for AR, VR, Metaverse, heavily recruit for, both professor and, at all level and also students. So, very good, if you have any student who are, looking for faculty position or, some master student looking for PhD that, welcome to contact us. Yeah.
We're also looking for a postdoc, by the way, if you
Also
have any close to graduation PhD student.
Yeah, it's, so we're putting tech people and art people together in the same department, so they have to work together. Okay, great. So thanks everyone. So
Fantastic.
yeah, we'll talk to you soon, very soon. Thank you.
All right. Bye. Bye, everybody.
Bye. Bye.
Thank you.
Thank you. Thank you. Bye. Bye. Bye.
Bye. Have a good one.
Bye.
Bye.